I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, Lord, to thank you for the students. Just pray that you'd help us to use this time wisely and to accomplish much for your glory, Lord. In your name I pray. Amen. Okay, so I'm still kind of working our way through some basic quantum mechanics. Of course, this is kind of the big deal. I h bar partial psi partial t equals to minus h bar squared over 2m partial squared psi partial x squared plus v psi. This is, of course, Schrodinger's equation. This h is super tiny. It is Planck's constant. Well, the h is Planck's constant. This is h bar, which is Planck's constant divided by 2 pi. And the notion here is that this is describing some sort of one-dimensional quantum state. You know, the probability basically that you measure the state being at position x at time t. You square that. I mean, this is the modulus squared dx. That's the probability in finding the particle between x and x plus dx at time t. Particle's got to be somewhere, so we want this condition. You know, this is the normalization condition. And the thing we did at the end of last time was I showed that if you normalized it for one time, it stays normalized, assuming it's a solution to Schrodinger's equation. So there's a consistency between Schrodinger's equation and the probability interpretation of the wave function. Then we talked a little bit about this being an eigenstate of position, this delta function. I'm not sure where to go with that from there, but that's kind of a quirky observation. And then I mentioned to you guys that a determinate state has uncertainty 0 and where it is. This is the uncertainty. Sigma sub q is the uncertainty in q. And so this shows 0 uncertainty for a determinate state. That's essentially by definition. But that forces through this mathematics here for a determinate state to be an eigenstate of the operator q. All right, so so I want to keep picking away here at the basics of quantum mechanics. Hopefully, if I do this right, we will take a look at the. There's a couple more things I want to look at with you guys. I want to look at the issue, and I probably won't really. You know, I was reading Griffiths, trying to gather my thoughts, and so basically there's two kinds of states he talks about. He talks about scattering states and bound states. I've mostly talked to you guys about bound states, but I've said a little bit about scattering states. Scattering states are a little bit trickier because basically he'll find a scattering state which is a solution. It's a solution to Schrodinger's equation, which is unbounded. But the kind of characteristic feature of these scattering states, at least kind of the natural ones that appear from separation of variables, is that they're not normalizable. So it's like, well, how do you get a solution that's got, you know, some sort of probability interpretation? Well, then what you do is you kind of take a packet of these scattering state waves, and you take like a bunch of them, you put them together, and you force them to sort of build like a little wave packet. And that's quite complicated mathematically, but I might be able to say a word or two more about that. All right, so I think I just need that mostly. See, another thing I can prove for you guys, and I think these kinds of little derivations are helpful, at least at the start, is that if we look at, all right, so here's the expectation value of x, all right? In other words, what value do we expect to find it in? Like, what's the average value of x that's observed if you keep, you know, observing this quantum state? So you take the integral from minus infinity to infinity of x times psi star psi dx. This is the expectation value of x, essentially by definition. So we can take measurements at future times. We can study how the expectation value of x changes in time. It's actually interesting to calculate dx, the derivative of the expectation value with respect to time, and see how that goes. All right, and we can use Schrodinger's equation to help with that. So let's do that, dx dt. So we're looking at partial t of the integral minus infinity to infinity of x psi star of xt psi of xt dt. All right. And okay, so I pull the derivative inside the integral. And then because we're taking partial with respect to t, I can pull x out. And then I'm going to have, let me just go ahead and, so you visualize it in your head, the steps. So then we get partial psi star, partial t, psi, plus psi star, partial psi, partial t, right? Using the product rule. And of course then we can do what? We can trade those. See what we can do up here? This can be rewritten as partial psi partial t equals to what? H bar over 2mi, right? I guess there's a minus. Partial squared psi, partial x squared. Oh, stink. Plus v over h bar I suppose, psi. Right?
Sorry, for the integral, isn't that still dx though?
Yeah, that is dx. Thank you. It was dx from the start. Thanks. Very good, very good. Excellent. I'm glad you picked up on that. Now, if you think about using Schrodinger's equation, right? So we're replacing, and I somehow have neutered my, I cut its feet off, I guess, and that's something else anyway. So there we go, I fixed it. Almost fixed it. So these are all supposed to be big size. All right, so all right. So if you just can visualize this and save me some writing, that would be awesome. So if you look at, you plug in, right, into like partial psi star partial t is what? It's h bar over 2m mi, conjugate of that, right? Taking the complex conjugate of that equation. So let's see what happens when we plug this and that into here. Can you see what cancels? So like the first one gives me like a minus v over h bar I psi star psi, because there's a psi here and there's a psi star in that. And then the second term gives me like a v over h bar I psi star psi. Right? The psi's commute, they're just complex functions, complex valued functions of a real variable. So the terms with the potential drop out. Those cancel. Right? And then you're just left with the second derivatives, which I'll write. Let's see here. I'll write the h bar. H bar over 2mi. And then that's partial squared psi star partial x squared psi minus partial, minus psi star partial squared psi partial x squared dx. And then what do we do? this point, we do some calculus. So this is the integral from minus infinity to infinity. I got this h bar over 2mi, which we're just going to leave out here, right? And I say you can rewrite that as let me copy it down. So what I say is that's the same as like minus partial x, all right, partial psi star partial x, psi, minus, you'll forgive my psi not having feet, psi star, these are all footed psis. Oh, there's one there, I put a foot on that one, I'm happy. So I believe one way you could look at what I'm doing right now is basically, it's product rule, okay? From another perspective, you could say I'm integrating my parts. All right. Try to appreciate what's going on here. So when you differentiate this, right, you get two terms. The one thing you get would be like the just x differentiates away, right? And you're left with partial x of this stuff, right? Now if you think about partial x of this stuff, it's exactly this up here, right? Because on the one hand you get the second partial derivatives, which we have up here. On the other hand, you get like the mix, just the partial psi star, partial psi terms. But those are zero here, right? So if you think about this grand glorious product rule, on the one hand you got this stuff, right? On the other hand, you're adding the my point is this derivative comes out to what I have up here already plus x times this stuff, right? So over here we subtracted excuse me, the point is this derivative gives me this plus that, right? So what I'm doing is it's integration by parts. I mean, I'm replacing this with, it's exactly, you know, d dx of ab, dA dx, b plus a dB dx, right? It's like this is that term, so to speak, right? And then this is that, and we're subtracting that piece. Anyway, getting to the point here, guys. This, right, if you integrate from minus infinity to infinity, provided that the wave function and its derivative, or at least the wave function is going to zero and the derivative is not misbehaving, well, it's hard to imagine a function that goes to zero and yet has a derivative which misbehaves. Okay, it's actually not that hard to imagine. It looks like this. Right? If you squeeze that thing down to, it's going to zero, yet its derivative misbehaves rather badly. And I assume that kind of thing could happen at infinity. Anyway, setting aside mathematical nonsense, go away. Stupid function. I hate you. Anyway, this integrates to zero, and we're left with this over here. That, of course, that's 1. And so what is that? Minus infinity. Got myself h bar. H bar. Why do I? Okay, fine. I brought the I upstairs. That gets me a minus h bar over 2m. H bar I over 2m. Partial psi star. Partial x psi. Minus psi star. partial psi partial x dx. This piece integrated to 0. So what can we do with this? So what I want to do is I want to have just these kinds of terms. That's what I decided. So how can I move the derivative from psi star to psi over here? Right? So this, right, we can write this, right, as this guy. Does that make sense? And so in so doing, this integrates to 0 on the boundary, assuming that the wave function, right, goes to 0 at infinity. And then, excuse me, I've got, looks like, minus h bar I over m. I don't have a 2 there. The 2 is gone because I got 2 of them, right? Because I got like the I've got this one up here already, right? That's still here. And then this one converts to that. So now I got 2 of them. The 2 cancels the half. I get h bar I over m. Integral from minus infinity to infinity. Psi star partial psi partial x, right? Dx. Now, incidentally, oh man, this is really cool. Do I have the m there? Is there m there? Is that right? There was no m on the. There's no m on the other side of Schrodinger's equation, is there? No. Sorry, just thinking about something. Huh. I wanted to see something here. It's not quite what I want, though. Oh! Cool. Check this out. So, m dx dt, right, equals to, check this out, guys, the integral from minus infinity to infinity of psi star, and then the operator, h bar over I, partial x, right? Acting on psi. In other words, this is psi h bar over I partial x acting on psi. Now that may not look significant to you, but to me it's really cool because the momentum operator, right, is actually represented by h bar over I partial x. And of course over here, you know, if I was to look at this a different way, I could say ddt of m, well, how to say that, I don't know. Anyway, to me that's, you know, like that's the expectation value. That to me looks like the expectation value of momentum, right? So how appropriate that the expectation value of momentum should be given by the bracket of the momentum operator. So in some sense, this is a partial perhaps a partial derivation that the momentum operator is h bar over I times partial x, or it gives you some reason why you might expect that momentum looks like that in the world of operators. There are other ways of coming to it, so I just wasn't expecting it, so I'm happy. Okay. Let me try to move on here. Alright, so what I say next here, and I don't, guys, I still don't know where I got these things from, because I've been looking at Griffiths, I haven't quite found it yet, so I'm not quite sure where some of this is coming from. Huh. Just following my notes here for a little bit. So continuing. So the intuitive leap, I say, is you might expect the expectation value of the velocity would be the derivative of the expectation value of the, and of course the expectation value of p would be mv. So I was just sort of advocating for this viewpoint. And anyway, with these definitions we have, oh yeah, so I'm saying these are definitions for me. With those definitions, of course, we have the expectation value of momentum is, oh, I'm sorry, now I'm in reruns. I'm just recreating what I already noticed. Sorry, guys. I guess I'm consistent in what I think is interesting. Yay, okay. And then, anyway, so the point here is the momentum operator we can look at as h bar over I partial x, whereas the position operator is just x. Okay, it's multiplication by x. So position operator is kind of boring. Both of these operators act on functions of space and time, x and t. Right, so like formally, x hat acting on f at the position, say x naught, would be equal to x naught f of x naught. Okay. And actually, that's still not good because I still need a time. And I'm not sure I put the time in the right order. But anyway. Blah, 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 blah. Enough blah, blah, blah. So I told you... Excuse me. There's, let me put it up here. So the expectation value of Q was equal to the integral from minus infinity to infinity of psi star, the operator of Q, psi dx. We also have a theorem. Maybe I'll prove this. This is known as Ehrenfest Theorem. And it may answer some of your questions. I think this theorem is very cool. It says that the time, shut up. The time rate change of the momentum is equal to the expectation of the partial derivative of the potential energy. So we like recover Newton's laws at the level of expectations. Like on the average, we recover Newton's laws. So another way of looking at that. All right. Apparently that was the end of a lecture for me. Now I got you guys a copy of Griffiths. I'm just waiting for it to come in the mail, so I found a place I could get it for pretty cheap. So I'm gonna...
No, it has a cat on it.
I do not believe it has a cat on it.
Yes, it does. It's got 2 cats on it.
I don't... Well, this one does, but I think the one in the mail will not.
You will draw 2 cats on it.
Yeah.
We'll take a lecture on that.
Alright, so let me try to wrap up this sort of business. And then we'll get back to specific examples. Like I want to get back to the square well or There's also something called the direct delta function potential, which is like just a spike potential, and it's actually pretty easy to solve, and that's probably worthwhile discussion to have. But we'll see. Anyway, I'm just trying to stay chill, and we get as far as we get, and I'm content with my life. All right, so Vervi. I wanted to show you guys. So this is a I love this calculation. I think it's really neat. But I will freely admit that because I also love theoretical integration by parts. Anything that involves theoretical integration by parts, it just makes me happy.
And complex numbers.
And yeah, it's all complex all the time here. That's true.
Did we ever find out what was wrong with that that Dirac formula that we were working with the other day?
Wrong.
Something was funny with it, but then we moved on.
Oh, yeah, I don't know.
I thought there was like
I forgot what was funny. So that's part of the problem.
yeah.
I actually do not
We erased
need.
it.
I actually do not need Schrodinger's equation for what I'm about to do, so I'm going to erase it. Oh no! Okay. Alright, so I will now attempt to derive for you the generalized uncertainty principle. Okay, so the generalized uncertainty principle, it relates, so you're given, oh come on. You're given, there we go, two quantum mechanical observables. And with so operator A hat and B hat. Alright? And to each observable we have a corresponding uncertainty. Right? Uncertainty.
Sorry.
That's okay. I can get far. So there's an uncertainty. We usually look at the square of the uncertainty. So this will be equal to the bracket of, let's see here, A hat minus the expectation value of A acting on psi with the same thing. And so Griffiths introduces a intermediate notation F with F. Okay, he's labeling that thing F. Basically, this is the F vector. Okay, the F ket. And then likewise, sigma b squared, right, is going to be GG, where G is B hat minus the expectation value of B acting on the wave function psi. Alright. And now he's about to invoke something. Okay, you ready? What are we going to invoke? We're going to invoke the Schwarz inequality. So invoking the Schwarz inequality, so we have sigma a squared, sigma b squared, which is, now this is not the Schwarz inequality, this is just notation, right? That's FFGG, right? What's that? That's greater than or equal to what? So the Schwarz inequality usually looks like for us guys, something like, here's the most sort of benign version of it. Well, that's not the Schwarz inequality, but of course this comes, this is, this. This thing, right guys? So if you square both sides of this, right, that gets us closer to what we're using over here. So like the length of A squared would be like FF. The length of B squared would be like GG. And then what we're about to put over here is that's larger than FG squared, right? Although more to the point, it's larger than the magnitude of FG squared. All right, there we go. Now, the complex inner product is generally a complex number, right? So what? So this right here, guys, is, you could call that Z, right? That's the real part of Z, plus I times the imaginary part of Z. You've read this in your reading? Okay, that's good. Anyway, any complex number you can split. What's that?
No, I said yeah.
Yeah.
You've done that.
Really? Sorry.
And then the imaginary part, though, we have a formula for, right? Like Z plus, Z star is 2 times the real part, and Z minus Z star is 2I times the imaginary part of Z, right? These are easy to derive. So, but also, fun fact, the modulus of Z is greater than or equal to the absolute value of the real part of Z, or the absolute value of the imaginary part of Z. You pick it. We can go either way here. Right, so what we're going to do, since I'm going to follow Griffiths, because so far he's done pretty good. Probably don't agree with him much in terms of philosophical things, but that's okay. I do like his books, despite disagreeing with his worldview. Let's see here. That's okay. Let's see here. Then this, right, this would be greater than or equal to, you pick it, either the real part, or we're going to do the imaginary part though, okay? So the imaginary part of Z. Right? But that is equal to 1 over 2I, and we get, let's go, FG minus FG conjugate, right? All of that squared. However, we can calculate, what can we calculate? Lots of stuff here. How about this? So F with G, what's that? This is A, minus expectation value of A, right? Psi with B hat minus expectation value B, psi, like so. I'm going to get rid of my complex musings. You already got them, right?
Yeah.
Okay. And then we can do some math on that. Let's do it. All right. After my experience in abstract algebra earlier today, I am unwilling to try to think out my own proof. Copy. Bad things have happened today. Bad things. I don't know. It wasn't so much that I said anything particularly wrong in abstract today. I just was generally dissatisfied with the volume of material I presented today. In the speed. And the specificity. And not enough extra tidbits. Okay, anyway, I digress. Let's see here. So,
Only they were in an hour and a half classes.
Let's see here. My next. Now, this is an observable, right? What does it mean? What does it make? What does that mean to say it's an observable? What did we talk about last time? For it to be an observable, it has to be Hermitian, right? The operators have to be Hermitian, which is just tantamount to saying that you can, in this formalism, you can move the operator from the ket, from the bra over to the ket. So I'm using the fact that A is Hermitian. And by the way, the multiplication, if A is Hermitian, it's also the case. I mean, this operator is a really boring operator. You know, this is like. Well, anyway, this is also Hermitian. Long story, uninteresting story short. Golly. And then distribute, all right? So we got like psi, A hat, D hat, right? Psi plus psi A hat, expectation B, psi minus state. Good book. Psi, where was I? Oh, minus A B hat psi, and then plus psi A B psi. Some of these things are just numbers, all right? So we can behave. I mean, like the difference. This is just a number. This is the expectation value of the operator B. So that's just a complex number, whatever it is. So we can treat it as such.
Does that cancel?
What's that?
Does that cancel? No wait.
There-
Never mind.
There
Sorry.
may be some
Go ahead.
cancellations in here, yeah. But not everything. Okay, so we're also assuming that the wave function psi is like normalized. We'll get to that in a second here. So this actually gives me, oh man, yeah, right. Our rule was that the sesquilinearity. We actually have linearity in the second in the ket, but we have conjugate linearity in the bra, in the sense that you can pull scalars out with a conjugate in the first one, but not the second one. So like this here, just goes to like psi, that hits it, and you end up with, if you'll allow me to just write down one step, this converts to this. Because remember the thing we proved over here actually. Remember that for an observable, the observable acting on the wave function gives me back the expectation value of the observable times the wave function. So, all right. So anyway, so that and then this one. Oh, maybe I'm. Oh, wait a minute. I'm a dummy. The thing is, I don't think I can't assume that the wave function, there's something I'm not supposed to assume here. He doesn't write it that way, he just leaves that one alone. It may be that I could do that, but I shouldn't do that in the interest of deriving an interesting inequality. You know, sometimes you can do something, but you just shouldn't for the sake of fighting an inequality. Maybe this is that thing. Okay, so this is straight up A hat, B hat by definition, okay? That's, in other words, you take this operator and you squish it by the wave function that gives you the expectation value of the product operator AB. This is just going to give me expectation value A, expectation value B, psi with psi, and this is going to give me plus expectation value A, expectation value B, psi. I believe I have made a sign error here. You guys find it for me.
This second part, second term maybe? In the second line? Second to last line?
Yeah, this one's supposed to be minus, right?
That.
Yeah.
Second term.
So that was supposed to be a minus. So these guys cancel. By the way, the wave function is normalized to 1, so this is 1, right? The psi with psi is it could be the integral from minus infinity to infinity of psi of x dx, right? But it's a more generalized notion than that. We don't always deal with a continuum. We can sometimes deal with like a discrete set of states or something. And then the psi stands for a sum over a discrete spectrum of states, or it could be a finite set of states or something else. Anyway, so here we go. We got A hat, B hat, minus, like that. And he says likewise, if you look at GF, what do you get? You get B hat, A hat, minus AB. I mean BA, I guess, but you know, they commute. Those are numbers. These don't commute necessarily, right? And so, conclusion, excuse me. Remember, what's this, by the way? That was GF, remember? That's part of the axiom for the inner product on the Hilbert space. So, long story short, what we have here is 1 over 2i, right? The expectation, so these terms cancel, right? And you're just left with the difference of, and these ones I'll just combine. We've got A hat, B hat, minus B hat, A hat. So therefore, for us, the uncertainty of A squared, the uncertainty of B squared, standard deviation, I think is what it's usually called. Square of the uncertainty is standard deviation. Although honestly, it's sad, but I forget these silly terms. That's greater than or equal to 1 over 2i, the expectation of the commutator of A hat, B hat, quantity squared. And that, folks, is the generalized uncertainty principle. All right, so for example, if we think about A equal to P hat and B equal to X hat, let's see what it gets us. P hat, X hat, right? Let's calculate the commutator of momentum and position. So to calculate a commutator, you should let it act on a test function. These are operators. That's the way to think about it. So what you're looking at there is P hat, X hat of F minus X hat, P hat of F, right? Now the P hat, as we have just explained, should be interpreted as H bar over I, right? Partial X. That X on X times F, because that's how X hat acts, right? And then over here we have minus x times h bar over I, partial x, acting on f, right? So what do you got here? Product rule. H bar over I f plus h bar over I x partial f partial x minus h bar over I x partial f partial x. This guy and this guy natural enemies. And so therefore we have derived the commutator of momentum, and the position operator is exactly h bar over I. Do you guys have any questions about that calculation there? So what's this say? This brings us to Heisenberg's uncertainty principle. This is the Heisenberg uncertainty principle that relates to position and momentum. So like the uncertainty, or usually you write something like the uncertainty we write as like change in momentum times the change in position squared, right, is greater than or equal to, and see what happens here? We have 1 over 2I, and then we've got ourselves an h bar over I, right, squared. But that gives us what? The i's give you -1, right? And so you got yourself h bar squared over 4, right? And so we get the change in momentum times the change in position is greater than or equal to, looks like h bar over 2. I believe that is the famed Heisenberg uncertainty relation. Yeah. Uncertainty in position times the uncertainty momentum has to be greater than or equal to h bar over 2.
I could be just being stupid right now, so why does that tell us what it does?
He says the uncertainty in X is sloppy notation and sloppy language for the standard deviation in the results of repeated measurements of identically prepared systems. Right, so if you, yeah. I'm sorry?
So, sorry, I could just be being stupid right now, but why does that tell us what it does?
Why does it tell us what?
Why does that tell us what it does? What the basic uncertainty principle does?
Well, it tells us that the uncertainty, the product of the uncertainty in momentum and the uncertainty in position for a one-dimensional quantum mechanical system with position x and momentum p.
So if we know more about one, we know less about the other?
Yeah, I mean it says you can't know both with infinite accuracy. There has to be you cannot know both at the same time. No can do. What that means, right? Because remember we just said last class is a determinate state has uncertainty 0, right? So let's extract some linear algebra from this. What this says is that you cannot find a simultaneous eigenstate. You can't find an eigenstate which is both an eigenstate of the position operator and the and the position operator. Excuse me, did I say position? The position and the momentum operator at the same time. In part, this is the reason for this. You know, we have derived a physical reason for that. It's because that would say that if they both were determinate states, then uncertainty in both would be 0. And that would violate this inequality we just found. Now in linear, I often will give a homework problem where I have you find this fact for yourself directly. If you have an eigenstate both of, if you have the eigenstate of two things that that don't commute, right? You can get contradictions. Let's see here, like. Oh, my brain's not working, but you can attack it directly at the level of linear algebra if you don't. I mean, the claim I made about eigenstates at the end can also just be seen from pure linear algebra. That you can't simultaneously diagonalize two operators unless they're... The only way you can simultaneously diagonalize two operators is if their commutator is 0.
Did you give us any sort of that problem last semester?
Maybe. Maybe not.
I don't recall.
All right, so let's see. You're continuing with this slugfest of abstract notation. Nice. So here's a somewhat another attack at the relation of like the expectation. This may be a derivation of Ehrenfest Theorem. We'll find out here in a second. What happens if we calculate the time derivative of, say, the expectation value of Q? He says, let's compute the time derivative of the expectation value of some observable. All right, so Q is a function of x, p, and t according to him. P is momentum. Now that's significant because the other way to write Schrodinger's equation in the world of that we're currently about to go into, this is Schrodinger's equation. IH bar, partial psi, partial t, is equal to Hamiltonian operator, psi. Right. So this H hat, what is it? It's the kinetic energy plus the potential on it, basically. The kinetic energy is the h bar over 2mi partial x squared, and the potential energy would be the so sad.
Physics lab.
Makes me sad too. And then potential energy, of course, is the potential, like the V. All right, just a Hamiltonian viewpoint. We'll talk more about Hamiltonian some other day, but anyway. All right, so here's the deal. So the derivative of the expectation value of Q would be the derivative of psi Q hat psi. Okay, nothing too controversial here just yet. And then he says that that is equal to triple product rule. Oh, cool. Check this out. Now, Schrodinger's equation does what? Oh, this calculation's really cool. Schrodinger's equation says that we can trade this for what? Minus I over h bar, right? H hat psi, right? Or if you prefer, just 1 over h bar I. I mean, I'm just solving this for partial psi, partial t, okay? And likewise this, we can solve for minus I over h bar Hamiltonian operator acting on psi, right? Alright, so then we have minus 1 over I h bar h hat psi q hat psi. I'm not sure I believe that. Because if I pull a constant out of the ket, I mean, the rule is if we have C psi, you know, psi or whatever like that, that's C star. Psi psi. I mean, that's the nature of the broadcast. So I don't see as I can pull that. Oh, is the I downstairs? Oh! Curses. You know what? Fine. 1 over I h bar. You happy? You happy? It's my expression versus their expression. It's confusing me. Okay, now I can see that he's pulled this out, but he's conjugated it. Okay. Good. And then this, well that's just the expectation value of the time derivative of the operator, right? And then this over here, I've got 1 over I h bar psi h hat psi. Where'd my q go? I'm an idiot. That's a qh, right? Qh bar psi. Now, the Hamiltonian is, guess what kind of operator is it? It's a Hermitian operator. Okay, so I can move that over there like that, right? And then I'll have minus 1 over I h bar psi hq minus qh psi. Like that. Plus my expectation value of the time derivative of the operator. And so what is that? That is I over h bar, bringing the I upstairs again, absorbing the minus. The expectation of the commutator of the Hamiltonian with the operator, right? Plus the expectation value of that guy. Let me write that again. That's the derivative with respect to time, total derivative with respect to time of the expectation value of the operator. He says this is an interesting and useful result in its own right. He's got a couple problems about it. He says in the typical case where the operator does not explicitly depend on time, it tells us that the rate of change of the expectation value is determined by the commutator of the operator and the Hamiltonian. Right? So what does that say about an observable whose